Okay, so next we're doing mutually and non-mutually exclusive events. Okay, so in other words, we're looking for, before we did A and B, now we're doing A or B. Mutually exclusive is the probability of one does not affect the probability of the other. Neither probability affects each other, and therefore the events, it's very simple to get their probabilities. You just take the probability of one of them and you add it to the probability of the other, and that gives you the probability of getting one or the other. Where non-mutually exclusive events is where they actually do affect each other, where there's overriding or overlapping in terms of the probability. So this looks like this in terms of Venn diagram, where A and B, see if that'll go. Nope, I guess not. A and B are both have probabilities, but there's also a bit of overlapping of A and B happening. And what will happen is we overcount something like that. So our formula is similar, except when they're non-mutually exclusive. Probability of A similar to above, plus probability of B similar to above, minus the probability of A and B both happening. Because otherwise we're double counting, and we assume our probability is too high in this case. Okay. So first we'll get through a mutually exclusive event. We're at a fundraiser, and they got 15 t-shirts. 2 are black, 4 are blue, 9 are white. And it just so turns out that you only like the black or blue t-shirts, you dislike white t-shirts. Okay. So what is the probability that you get a shirt you like? So probability you get a shirt you like. This is probably we get a shirt I like. Well, we know there's 15 t-shirts, and I like black, so the probability of, we'll call this event A, this will be event B, and we can almost refer to this as event C, right? The probability of getting event A or getting event B, right, one or the other, we don't have to get both, is just the probability of event A plus the probability of event B, because there's no overriding. If I get a black shirt, it doesn't take away from the blue shirts, and if I get a blue shirt, it doesn't take away from black shirts. So probability of event A is just 2 over 15, plus the probability of event B, which is the blue shirts, is 4 over 15. But we have a common denominator, so not much to do. Our probability is 6 out of 15, which makes perfect sense, right? Because if we just kind of put these together, well, I know I like all of these shirts. Well, that's 6 shirts out of a total of 15. So it's very logical in that sense, right? And the probability of getting a shirt you don't like, assuming you are going to win, okay, we're assuming that you do get a shirt for sure, is 9 out of 15. So you have a better chance of getting something you dislike than like. Let's bring up another event that's non-mutually exclusive. Now this is going to be an event that's a little different from the one we've just done. Cards are selected from a deck, okay? So we're assuming this is a standard deck of cards. Do you know how many cards are in a standard deck?
52.
52, right? The probability of getting either, that's important. Either means one or the other. So not getting both. A heart, it's probably getting a heart. Or a face card, which represents what? Jacks?
King and queen.
Yeah, queen and king. Okay. Great. Well, hearts, our decks are divided into 4 sections, right? Out of the 52 cards, we have 4 sections. You either have a heart, you either have a diamond, a club, or a spade. Okay? Which means essentially each of these decks holds 52 divided by 4. In which case is what?
13.
That's right, there are 13 cards. So the probability of getting a heart, probability, if we're going to call that event A, is 13 out of 15. There's our event A. Event B is face cards. Okay. Well, how many face cards are there? Well, we know there's 3, and then there's 4 decks, right? So 3 per deck.
3 times
4 gives us 12. So there are a total of 12 face cards. In other words, 12 out of 52 is the probability of event B happening. But, okay, what ends up happening there, if you think if we count them individually, is we're double counting the jack, queen, and kings of the hearts. Okay? And I'll kind of show you what that means. So for instance, let's say we have a whole bunch of cards. I'm going to quickly represent 13 red cards. So 13 red cards. So let's say 1, 2, and just to speed this process up. Okay, so 3, 11, 12, and put that up there, 13. Okay, so these are all hearts, we'll say. These are the probability of event A, and we know all of them. We have an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and the king, right? That was our probability of event A. Event B, probability of event B, well, we have several different types of cards, right? We have our jack, queen, king from diamonds. We'll do the actually red for hearts. Jack, queen, king from diamonds, we'll do an orange, just so something's different, okay? So we can tell the difference. Jack, queen, king from Jack, queen, king from fill color. Spades we'll do in black. We'll write them above. And the jack, queen, king from clubs we'll do purple, so it's a dark color. 1, 2, 3. I know that's the same size, but here's the ideas that are important. Well, we know we have a jack, a queen, a king. We have a jack, a queen, a king. Jack, queen, king. And finally, jack, queen, king. Well, the problem is this is our 12 out of 52, and this is our 13 out of 52. If we were to just add these together, what ends up happening is we're double counting this jack, queen, king, because we're counting them twice. Okay? We do need to count it once, right? But if we get the heart of a king, it doesn't increase our probability. It doesn't make it any better for what we're doing. So in other words, our probability of event A or B happening is a probability of A, which in this case was 13 out of 52, plus the probability of B, which is 12 out of 52, but subtract, what is A and B? How many?
3.
Yeah, there are 3 cards. Subtract 3 out of 52. So we take 3 away from the 12, that gives us 9. 9 plus 13 is 22. So our probability of those two events happening are 22 out of 52.